Hello, I'm Mrs. Edwards, and today we're going to find the derivative of trig functions. As we go through, you want to make sure that you write down the derivative of each of the trig functions, but ultimately, these derivatives should be memorized. Let's start here with the derivative of sine. The derivative of sine of x is equal to the cosine of x, and the derivative of cosine x equals negative sine x. We're not going to go through every single trig function and draw its derivative, but let's do at least one. We have in the past taken a function and then graphed its derivative from that function. So this is a good opportunity to practice that. Here is a picture of the graph of sine of x. Starts at 0, 0, and then heads up and completes one cycle every 2 pi. If you don't know what the graph of something looks like, well, a great fallback plan is, of course, just plotting several points and connecting the dots. So that's exactly what we're going to do. We're going to start here at 0, 0 and work our way to the right, finding the derivative and plot some points. So if you were to evaluate the function f at 0, the sine of 0 equals 0. The derivative is the slope of the tangent at x equals 0. So the tangent line slope there at x equals 0, that tangent line has a slope of 1. So at f prime of 0, it equals 1. So we now know one point on the derivative function, so I'm going to plot the point 0, 1. Let's repeat this process as we work our way to the right. Okay, the next point we're going to take a look at is what would the function be if we evaluated at pi over 2? Well, the sine of pi over 2 equals 1. The derivative of the function at pi over 2 is the slope of the tangent at pi over 2. And the slope of the tangent there is 0. So we have another point on the derivative function. We can plot the point pi over 2, comma 0. A reminder of a cool feature there is remember that when you graph the derivative of a function, the minimums and maximums turn into x-intercepts, and that's exactly what happened there. At pi over 2, we had a local maximum, and that turned into an x-intercept. Okay, here's another point. How about evaluating sine of x at pi? Well, the sine of pi is equal to 0. And the derivative there at pi, the slope of the tangent at that point, the slope of that is negative 1. So here we have a third point to plot for the derivative function. So pi comma negative 1. Keep on going here. Another important point would be at pi over 2. The function evaluated at 3 pi over 2 is negative 1. The sine of 3 pi over 2 is negative 1. But the slope of the tangent at 3 pi over 2, we're at a local minimum. So the slope of the tangent there is 0. So a point we now know on the derivative function is 3 pi over 2, comma 0. Let's go for just one more. If I evaluate the sine of x at 2 pi, the sine of 2 pi is 0, and the derivative there at x equals 2 pi, the slope of the tangent right there at 2 pi is positive 1. So we have another point. So if I plot the point 2 pi, comma 1, and then connect these dots, notice we have the cosine function. So the derivative of the sine of x is equal to the cosine of x. Couple other observations, just really some reminders, is notice how the original function sine of x, it is increasing from 0 to pi over 2. And all of the points from 0 to pi over 2 are above the x-axis. The local maximum turned into an x-intercept, all the way from pi over 2 to 3 pi over 2. the function was decreasing. And notice between pi over 2 and 3 pi over 2, the graph of the derivative is below the x-axis. Okay, and then right there, at 3 pi over 2 up through 2 pi, the graph of sine of x is increasing, and the graph of its derivative is above the x-axis. Right here at pi, that is where the slope of the tangent is the steepest. So notice here at pi over 2, the slope of the tangent was 0. And then as we move to the right, if we started drawing in slopes of the tangent, they would be becoming negative, and it would be more and more negative. And right there at pi, that's the steepest that the curve is. And as we move past that point and draw in slopes of tangents, they're still negative, but they're less steep. So this is a point of inflection. It's where we change from concave down to concave up. Coincidentally, it was on the x-axis, but that's not significant. That point of inflection turned into a local minimum. When you're memorizing the derivative of sine of x is equal to cosine of x, and the derivative of cosine of x is equal to the negative sine of x, the hardest part is going to be to remember that the answer to sine is a positive cosine, and the derivative of cosine is a negative. I've got a lot of silly stories for memorizing, and I'll be honest, it's a little tougher when I'm not in person here. But I will just say that all of my trig memorizations are based on that the sine function is this happy, positive, wonderful, good trig function. And cosine is a negative, mean, nasty function. So in that sense, like I saw the sign and I opened up, sine, positive. Okay, it's not sin. Ooh. All right, so sine, so when we're taking the derivative of sine, we're going to get something positive. Cosine is that mean, nasty little function, and when you take its derivative, you're going to get something that's negative. However you decide to memorize that, you want to really focus on how you're going to remember the answer to derivative of sine is positive and the answer to cosine is negative. All right, let's go ahead and put those to work. Let's say I want to find the derivative of y equals x to the third plus 2 sine x. Well, the derivative of x cubed, we can just use the power rule. The 3 goes to the front, subtract 1 off the exponent, so we have 3x squared. Okay, next, we have 2 multiplied by the sine of x. We have two things multiplied together, so you might think, ooh, I should use the product rule. But the shortcut there is when two things are multiplied together and they don't both have x's in them, you don't have to use the product rule. 2 is just a constant, no x's in there. So 2 is a constant multiplier, so you can just set 2 off to the side in your mind, find the derivative of sine of x, which happens to be cosine of x, and multiply the constant multiplier back through. So that is just 2 cosine of x. All right, then the next one, the derivative of x squared using the power rule, 2 goes to the front, subtract 1 off the exponent, so we're going to have 2x. Now this next piece is negative 1/2 multiplied by the cosine of x. So again, that negative 1/2 is a constant multiplier, so it's just hanging out there. We want to find the derivative of cosine of x and then multiply that by the negative 1/2. So the derivative of cosine x is negative sine of x. So if we have negative sine of x multiplied by negative 1/2, that's going to make that plus 1/2 sine x. Here are the other 4 derivatives of trig functions that you need to have memorized. And I'm sure you're thinking, how in the heck am I going to remember these derivatives? Well, first, write them down. Let's start there. And I'm just going to run through those really quick. Derivative of secant of x is secant of x multiplied by cotangent of x. Derivative of cosecant of x is -1 times the cosecant of x times the cotangent of x. The derivative of tangent of x is secant squared of x. I hate this notation. I know it's so pretty because it's compact, but I am it's like, I can't emphasize this enough to you. It's a great way to write your final answer because it's so pretty and compact. But if you are working with these trig functions, when you see this kind of notation, immediately rewrite it as, in this case, secant of x in parentheses to the second power. Because secant squared of x means secant of x multiplied by secant of x. Students sometimes see secant squared of x and think that that's the same as secant of x being squared. Okay, so rewrite it as secant of x to the second power. Similarly here for the derivative of cotangent. It says negative cosecant squared of x, which is a very nice compact way of writing it. But when you're actually doing some math, on it, you're taking derivatives and integrals later, you want to write this as -1 cosecant of x in parentheses to the second power, because it's -1 times the cosecant of x times the cosecant of x. All right, now getting to memorizing these four. There's a lot of cockamamie ways out there, frankly, to memorize these. And in most cases, I've kind of come up with my own silly ways of doing it. But I really like Calculus for Dummies' way of memorizing these four, so I'm going to share that with you. Also, a side note, I love Calculus for Dummies. What a fantastic read. It is such a misnomer. Obviously, if you're reading about calculus, you are no dummy. But gosh, they really have a really nice way of putting things. I would highly recommend it. Those of you that are taking this in high school, I know that in your English classes you have to read on your own a lot of different genres. Well, I think that's a book report you're going to get an A+ on. So you could get 2 birds with 1 stone and read that Calculus for Dummies book and write a math book report. Oh my gosh, I love it. Okay, so here we go. Psst, psst. Let me tell you the answer. All right, so this device here, it's all about the SST in here. And this device is not to help you with the easy derivatives. Derivative of sine is cosine, derivative of cosine is negative sine. This is to help you with all of the difficult ones. So the SST, the S stands for secant, and the T stands for tangent. So the first thing that you do is you just write secant, secant, tangent straight across from each other. Okay, so that kind of gets this visual going. So psst, secant, secant, tangent. Then directly below these 3, you write their co-functions. That is not memorized. Come on, people. Secant, just put the word co in front of it. What is secant's co-function? It would be cosecant. And what is the co-function of tangent? Cotangent. All right, so I just dropped down here the co-functions below. The next thing to build this is you're just going to put arrows facing in. All right, so I'm going to put some arrows just facing in there. And then the last piece is just to put a negative in the bottom middle. Now you do have to remember how to make this little diagram. So psst, SST, secant, secant, tangent, co-functions directly below. Co-function of secant is cosecant, cosecant, and cotangent. Arrows pointing in, negative, bottom, middle. Now we have everything we need for the derivatives. Just follow the arrow. Let's start here. If you have secant, the derivative of secant, follow the arrow. The derivative of secant is secant times tangent. Okay, start on this side. What is the derivative of tangent? Follow the arrow. Secant times secant. Ooh, secant squared. What is the derivative of cosecant? Follow the arrow. negative 1 times cosecant times cotangent. So negative cosecant, cotangent. And then one last one, starting with cotangent. What's the derivative of cotangent? Follow the arrow. Negative 1 times cosecant, negative cosecant squared of x. Bam! That's not too bad. Not to mention, when we get to integrals, you will have another 4 difficult integrals memorized knowing this little diagram. So be sure to jot that down and start practicing, just even in your mind a couple of times a day. What's the derivative of sine, cosine, secant, cosecant, tangent, and cotangent until you have that down, because you do need these ones memorized. We're going to run through 4 practice problems. 3 of the 4 have trig functions in them, and then I threw in an extra fraction one because I think you need some more practice there. All right, find the derivative. First thing you need to notice is that we have 2 things multiplied together, and they both contain an x, which means we're going to need to use the product rule. Here times the derivative of there, here d there, plus there d here. All right, so let's put those in. Y prime equals, here is x to the third. The derivative of sine x is cosine x, plus sine x, and times the derivative of x to the third, that's 3x squared. We have the calculus done. We might want to simplify just a bit. Please do not commit the algebra atrocity of calling that sine of 3x to the third. No, 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 no. Okay, trig functions are like bricks. You can't distribute something through them. So I'm going to rewrite that as 3x squared out in front of that sine x, and that's as simplified as it gets. Here we have another one, sine of x over x to the 4th. 2 things are being divided. They both have an x in them, so we're going to need to use the quotient rule. Low-D high minus high-D low over low squared. Start low, end low, over low squared. All right, so low-D high minus high-D low over low squared. When I go with low, that's x to the 4th. D high, the derivative of sine x is cosine x, minus high, which is sine x. D low, derivative of x to the 4th is 4x cubed, all over low squared, x to the 4th squared. Simplifying here, down here we have x to the 4th the second, power to a power, power to a power, multiply. All right, so that's going to be x to the 8th power. We're also going to be able to factor out something in common. In the numerator, in the before and after the minus, we have an x to the 3rd in common that we're going to be able to factor out. Okay, so factoring that out, and now that x cubed over x to the 8th, x times x in the numerator, in the denominator x times x, and we have 8 of those listed out. So 3 of those cross off, and we end up with an x to the 5th in the denominator. Okay, next one. We don't have any trig functions in this one, but again, I just thought we needed a little more practice. I don't care what the context is of the problem, whether we're adding, subtracting, multiplying, we're not even doing calculus. When you see a fraction within a fraction, the very first thing you should do is get rid of those fractions within fractions. To do that, you look at what I call the mini denominators, these little ones here. Obviously, x plus 5 is in the denominator, but these fractions within fractions, where are the denominators of those little fractions? And in this case, it's just x. So what you do with that little mini denominator is you use it to multiply the numerator and denominator by that mini denominator. Okay, so I'm going to multiply the entire numerator by x and the entire denominator by x, and that is going to get rid of all these fractions within fractions. So x multiplied by 3, that's 3x. X multiplied by negative 1 over x, that's minus 1. Okay, so we just distributed the x through the numerator. We need to do the same thing in the denominator, x multiplied by x, that's x squared, and x multiplied by 5, That is 5x, and that looks a lot better. Okay, we haven't done any calculus, we just cleaned up the original. Okay, we have two things being divided, and they both have x's in them. So low-d high minus high-d low over low squared. Start low, end low, over low squared. Quotient rule. So I'm just doing that quickly. Low, x squared plus 5x. D high, the derivative of 3x is 3, and the derivative of minus 1, a constant, is 0. Minus high, so 3x minus 1. D low, derivative of x squared is 2x. Derivative of 5x is 5. All over low squared. Okay, the next thing I can do is FOIL 3x minus 1 times 2x plus 5, and after I multiply those together, distribute a negative through each of the terms, and then multiply the 3 times each of those. Okay, so I multiplied the 3, got 3x squared plus 15x, FOILed that together, distributed a negative, combined like terms, and boom, there's our answer. Last example, a few more trig functions. Okay, so we have a fraction. So hopefully some of you are immediately thinking, oh, that's probably quotient rule. But we can save ourselves some time. When you have two things that are being divided, if they both have x's in them, then you're probably going to use the quotient rule. I could think of this as 1/6 multiplied instead. Also, the reason why I'm going to avoid the quotient rule is anytime you have a single term in the denominator, you also try to multiply by 1 over that to get rid of the quotient rule. Okay, but nonetheless, dividing the entire numerator by 6 is like multiplying the entire numerator by 1/6. Now that we have the derivative, let's find f prime at pi over 4. We would just go in and substitute all of the x's with pi over 4. I rewrote, notice, secant squared of pi over 4 as secant of pi over 4 to the second power, because that squared there really means secant of the x times secant of the x. Okay, next I'm going to go to the unit circle and go to angle measure pi over 4. Cosine is the x coordinate on the unit circle at pi over 4. And then secant is the reciprocal function for cosine. So you go to pi over 4 on the unit circle, and then you take the reciprocal of the x coordinate, and that's the answer to secant. All right, so I'm going to have 1/6 root 2 over 2. Again, that's the x coordinate at pi over 4, plus 1/6. And then secant of pi over 4 is the reciprocal of the x coordinate at pi over 4. So that's 2 over root 2. Doing some simplifying, multiplying 1/6 times root 2 over 2 is root 2 over 12. And then here, 2 over root 2 times 2 over root 2 is 4 over 2. And 4 over 2 is 2. So we multiply these two together. I'm going to go ahead and keep the denominator 12 and not simplify, just so that I can combine. So my final answer is root 2 plus 4 all over 12. This is the slope of the tangent to the function f of x at pi over 4. Bonus round. If you are in my class, feel free to stop the video here. I just have 2 more problems that might help some people out. They're not coming in nicely. They're just solutions that I've written to some problems previously. If my g function was the 4th root of t, I would want to rewrite that as t to the 1/4 power. Okay, then taking the derivative, exponent to the front, subtract 1 off the exponent. So 1/4 went to the front, and 1/4 minus 1 is to the negative 3/4. Here, 6 times the cosecant of t. So 6 is a constant multiplier, and the derivative of cosecant, okay, coming over here to our little device, the derivative of cosecant is negative cosecant times cotangent. So that was replaced with negative cosecant cotangent, making it minus 6 cosecant of x cotangent of x. I did get rid of the negative exponent there by moving the t to the negative 3/4 to the denominator. So 1/4 multiplied by 1 over t to the 3/4, numerator times numerator, denominator times denominator, and there we have the derivative. One other quick example, again, you do not need to take notes on this if you were in my class, just a quick bonus round in case it helps somebody. If we want to find the horizontal tangent, remember a horizontal tangent just means the derivative, the slope of the tangent, the derivative is 0. So if you're asked to find a horizontal tangent, you want to set the derivative equal to 0. That is not the be-all end-all though. This is a great example where you still have to verify after you go through process. Okay, so I did a low d high minus high d low over low squared. Frankly, I could do that faster because I could have written this as 2x over x squared minus 1 over x squared, which would have given me 2 over x minus 1 over x squared, and 2 over x is 2x to the negative 1 minus x to the negative 2, and I could use power rule. Okay, nonetheless, blah, blah, blah. I found my derivative using the quotient rule, and once I have this part right here, the only way a fraction equals 0 is if its numerator equals 0. So to get from this line here to this line, I just set the numerator equal to 0. And when you solve 2x equals 0, you get 0. And when you solve x minus 1 equals 0, you get 1. So these are the possible places where the derivative is going to equal 0. However, looking here, if you were to substitute 0 back up here, you would end up getting negative 1 over 0, which is undefined. That is because we have a vertical asymptote there. If you substitute 1 back into the original, you get 0 over 1, and that is truly equal to 0. So once you have these answers, anytime you have an x in the denominator, there can be some domain issues. So it's essential that you substitute the number back into the original to make sure you have what you think you have. All right, maybe this helped. No worries. Again, no need to take notes on these two. That was just a quick rundown. All right, have a great day.